Okay, so let's get started. And this is the seventh live session for applied linear algebra. And as usual, we will be solving some sample questions related to the contents that were covered in week number 7. And broadly, to summarize, week 7 started with the notion of music, right? It's not the conventional traditional music that you're used to, but in fact it's visible on the screen only. It stands for multiple signal classification, and it's an algorithm that we have actually seen primarily used for the direction of arrival, the DOA's estimation in a multi antenna system, right? So then we moved on to the estimators. Particularly we studied the we have already seen the MMSE estimator, minimum mean squared error, one that minimizes the mean squared error, and modified version of that is the linear minimum mean squared error estimator, which we have seen in week 7. And also then we saw the strategy for optimal power allocation for a MIMO channel, right? And that algorithm was known as the water filling algorithm. So we have a threshold, we have a water level, and based on that, depending on the strength of the channel, we allocate the powers to the individual channels, because essentially we have multiple channels, right, in a MIMO system, and we want to allocate power such that it optimizes the capacity overall rate, right? So uh, so we have seen these things, and of course we can't allocate negative power. That's what we have to keep in mind. It is at least 0. That's the lowest possible value the power can take. And I think, yeah, that's overall what we have seen in the week 7. So let's go ahead with the problems for today. And by the way, to introduce me once again, my name is Avik Mukhopadhyay, and I'm a PhD research scholar at the Department of Electrical Engineering at IIT Madras, and I'm one of the TAs for this course. So I'll be available every Fridays, 6 to 8 p.m. to walk you through some sample problems, which hopefully will help you to solve the weekly assignment questions. Okay, so let's get started. Switch to the other tab. So okay, although I'm writing week 7, but it's more precisely session number 7, but the topics are centered around week 7 contents. So let's start with the first question. So yeah, the first question, in fact, it's a straightforward factual question, which states, okay, what is the purpose of using the music algorithm? So music, as I said, stands for multiple signal classification, and we have seen the setup, right? We have multiple antennas, L number of antennas at the receiver, and there is an incoming input signal from some source. It could be an approaching aircraft or anything, or a target, right? So, and we have to estimate the direction of arrival of that signal, that theta, right? And we assume that every antenna is equispaced. Okay, the separation between the antennas is uniform, and it's a uniform linear array of antennas. And we have looked at the mathematics of it, right? We have represented the entire output, uh, output vector as a matrix form. So, and during that numerical analysis, we have looked at the what do you call that, the array response vector, right, or the array steering vector, so which involved that theta term, which is the angle of arrival. And although this question has nothing to do much with the mathematics, it's just a factual question, and by this time you already know the answer. Okay, and option A and B are never the right answer because this has nothing to do with actual music, but it's actually used for estimating the direction of arrival, the theta. in a multi-antenna system, right? So option D is the right answer, and option C is more related to the SVD approach. So we have seen SVD in MIMO, right? It what it does is basically it converts a decoupled, sorry, converts a coupled system to a decoupled system. So which, you know, using this spatial multiplexing and all, we can achieve capacity and improve the data rate. So, but music is used for direction of arrival, that DOA estimation. So straight away, this actually is option D. Okay, so music, which is multiple signal. By the way, please interrupt me if anything is not clear, or if my handwriting is not understandable at all. So yeah, so this music algorithm is used for direction of arrival. It's also abbreviated as DOA, as we have seen in the lectures. DOA estimation in a multiple antenna system. Okay, so nothing fancy about this. Now let's look at the second question. So okay, so the second question is based on optimal power allocation, and so again, as you see, there are connections to the SVD as well, because the MIMO channel matrix has been converted to the SVD form. And if you remember, the matrix that sits in between U and V Hermitian was the diagonal matrix, right? The entries of which are the singular values, and they are arranged in the decreasing order, right? So as you can see here also, the singular values of the MIMO channel matrix are sigma 1 and sigma 2, and sigma 1 is 2 root 2, whereas sigma 2 is 2. So clearly sigma 1 is greater than sigma 2. So they are arranged in the decreasing order, and the noise power is given as sigma squared, which is equals to 8. Total power is given as 9, okay, capital P. And given this information, you have to find the optimal power allocation strategy to maximize the capacity of the MIMO channel. Okay, and there is also one information which is mentioned, that we have to assume that okay, positive power allocation happens to both the channels, that is Pi. P suffix I is the power allocated to the ith channel, is strictly positive. Okay, that is the constraint. Okay, so in this case there are basically two channels, right? So we have to find what is P1 and P2. Okay, so I'll write down. So again, the strategy, what is the algorithm known as? If you recall, it's the water filling. Water filling algorithm. Okay, so why the name? Because like the power that is allocated, if you remember, was the difference, right? You have some, you know, different channels, let's say channel 1, channel 2, channel 3, channel 4, and so on. Okay, and there was that line threshold, right? If you remember, so this was, let's say, the threshold. So the power that is allocated to the first channel is this difference in the water level, so it is treated as a water level. Similarly, this channel is allocated this much power, third channel is allocated this much power. For the fourth channel, as you can see, it already exceeds beyond the threshold or the water level, okay, which is denoted by this orange dashed line. So since it sits already above the threshold, it is allocated zero power, no power at all. And the strategy says that I won't use that channel for transmission of any symbol, okay. And for the other channels, I am giving some boosts, I am giving some power, allocating some power in an optimal way that optimizes my overall capacity of the channel, okay. And that's what happens in, you know, this multi-carrier systems, where you have, you know, the multiple channels with different strengths of SNR, right? So you can think of it as, you know, this let's say this is channel 1, this is channel 2, this is channel 3, this is channel 4. So each of the channel are experiencing a different SNR characteristics. For the channel 1, I have slightly, you know, on the lower side. So the strategy is that if it has got lower SNR, then I'll give it more boost. So as you see, the difference from the water level to that height of channel 1 is more. And similarly, channel 3, as per the diagram, has the lowest SNR. So I'll give it the maximum boost. So yeah. Perhaps I don't think the explanation was good, but yeah. Hello.
It's okay, sir. It's okay. Yeah, we're able to follow.
Okay. Thanks. But yeah, I think the explanation, I don't think it was. I'm not, I mean, personally satisfied with the explanation that I gave. But anyways, we don't need a detailed knowledge of the scheme, but here we need to find basically the power that has to be allocated
Power
to the
that
two
has
channels,
to be actually.
right? So sigma 1, okay, just a second. Okay. Okay, sigma 1 is given as 2 root 2 and sigma 2 is given as 2. So these are your singular values of H. Remember that H channel matrix, MIMO channel matrix, and clearly sigma 1 is greater than sigma 2. Okay, and the noise power is sigma squared, which is 8. Also, the total power is denoted by capital P is 9. Now I have to optimally allocate power. So what does the water filling algorithm tell you? It tells you that the power that is allocated to the ith channel, so this denotes power allocated. Actually, the reason why I was not okay with the explanation before that, I used the diagram, but the diagram is fine, there's no issues with that. But I mean, if you take some other courses like wireless communication and so on, I think the strategy is like, I will use the good channels, okay, the channels which have a better SNR condition, I will use them, and I won't transmit using the channels which are having poor SNR conditions. Okay, that's the strategy actually. So that is the point to remember. So which makes sense, right? I will allocate power to the good channels which are having good SNR conditions, and I won't allocate any power for transmission to the channels which are having poor SNR condition. That is the overall takeaway. That's what I think I tried to uh, uh, dictate there. So Pi is the allocated power to the ith channel. Okay. To the ith channel. So and it has also been mentioned in the question that you see in the bracket that Pi is positive. We are taking Pi is strictly positive. Okay. So the general strategy says that Pi, power allocated to the ith channel, is given by this 1 by lambda tilde. Remember that lambda was that Lagrangian, because it's a constrained optimization problem that we are solving during the lectures, and that lambda came from that, right? It's the Lagrangian term. And lambda tilde is also, I think, log base 2 e times lambda, something like that. It's a function of lambda. So it doesn't matter, it's just some parameter, minus sigma squared by sigma I squared. So sigma squared, you know, it's the noise power, and sigma I squared is the ith singular value squared. This plus, now what does this mean, this plus notation? It means that in general, if I have some, let's say some x plus, let's say, okay, it means that it takes the value x, right, whenever x is greater than or equals to 0, and it is 0 when x is negative. So the least it can take, the value this x plus can take, is 0. Or in other words, how can you represent this x plus? It is basically the maximum out of x and 0. Got it? So this is the power allocation strategy. And why are we keeping the minimum to be 0? Because we can't allocate negative power, right? That is absurd. So but what I am saying is, in this question, that Pi is greater than 0, that is given to us. Okay, so this is not 0. So the whole parameter inside this bracket is actually greater than or equals to 0, actually greater than 0, strictly positive. That's why my Pi is taking positive value. Okay, so since this term is strictly positive, this is simply 1 by lambda tilde minus sigma squared by sigma I squared, right, based on the definition of x plus. Okay, so my Pi is 1 by lambda tilde minus sigma squared divided by sigma I squared. This I know, and I think similar example was discussed during the lectures also by professor. So now we have to basically put I equals to 1 and I equals to 2 and find P1 and P2. Okay, so but you might wonder, okay, how do we find lambda bar? How can we find lambda bar? For that we need to use the total power constraint. So if you put I equals to 1, what happens? This is 1 by lambda bar minus sigma squared by sigma 1 squared. So this is 1 by lambda bar minus sigma squared is how much? The noise power is 8. and you have to be careful here. Okay, so in this case they are in the linear scale, so this is just 8, okay, and total power is 9. It's not mentioned that it is in dB or anything. Here they are dimensionally same. If let's say some quantity was in dB and the other quantity is in linear scale, you have to ensure that both are in the same scale. If one is in dB, then convert into linear scale, and then you can take their ratios and so on. So you have to be a bit careful. In this case there is no complicacy, but sometimes we are often specify the values in dB, right? So for example, like how much is 100 in dB scale? If I ask you, if I have 100 in linear scale, how much does that correspond to dB in the log scale? What is the rule? You basically do 10 log base 10 of this thing, okay, and that will give you 10 log base 10 of 100 is how much? 2. So 2 times 10, that is equals to 20 dB. This is in the decibel scale or the log scale, okay. Sometimes you might have to do all these kind of conversions, but here we are good to go. We don't need anything, okay. All right, so this is, and sigma 1 squared is how much? Sigma 1 is 2 root 2, so 2 root 2 squared gives you 8. So this is 1 by lambda tilde minus 1, okay. So I'll call this as equation 1. Similarly, I can write P2 as 1 by lambda tilde minus sigma squared by sigma 2 squared. So again I can substitute the values. Sigma squared is 8 and sigma 2 squared was I think 2. I mean sigma 2 was 2. So sigma 2 squared gives me 4. So this is 1 by lambda tilde minus 2. Let me call this equation 2. Now as I said, in order to find this lambda tilde, the total power constraint has to be used. So the total power constraint, what does it tell me? That my total power, which is the sum of P1 and P2, should be equal to the total power, which is denoted by P in our case, and I think it is equal to 9, right? So from 1 and 2, if I add them up together, so what do I have? This plus this equals to P, and P is how much? It is 9, the total power, and that is nothing but 2 by lambda tilde is equal to 12, okay. So that gives you 1 by lambda tilde is equal to 6. Now you can back substitute this in equations 1 and 2. So now substituting 1 by lambda bar equals to 6 in equation 1 and equation 2, we can get P1 and P2, right? So yeah, so P1 we will get as 1 by lambda tilde minus 1, which is 6 minus 1. P1 is 1 by tilde minus 1, which is 6 minus 1, which is 5, and P2 is 1 by lambda tilde minus 2. This is 1 by lambda tilde minus 2, so this is 6 minus 2, which is 4. And you can see that clearly both of them are, like, of course non-negative, and in this case strictly positive, which was the assumption, and it follows the assumption. And so what is the final answer? It's P1 equals to 5 and P2 equals to 4, and of course if they are added, it gives me the total power, which is 9. So this is my optimal MIMO power allocation, okay. And as I said, see, channel 1 is allocated slightly greater power than channel 2, which makes sense because the singular value for channel 1, which was sigma 1, was 2 root 2, was the greater one, but sigma 2, which was the singular value corresponding to the second channel, was 2, which is the lower value. So as I said, and that that gives me the strength, right? I mean, if you remember that SVD technique, or even that PCA technique also, we pick the, that's why we arranged in the descending order. So the larger ones are the principal components, right? If you remember. So we, in PCA technique also, we use the P largest eigenvalues like that. So it makes sense to allocate more power, that's why, to the first channel as compared to the second channel, and which follows here, right? So, and that's what tallies with the water filling algorithm as well, as I said, right? So the channel which is in a better SNR condition will be allocated more power, so I'll use that channel to transmit, whereas the channel in a poor SNR condition will not be used. If it's in a very poor condition, I won't allocate any power at all to transmit. That's the strategy. And if you check with the options, it is 5 and 4, so option C. Okay, is there any question?
No.
Okay. Okay, so that is the second question, and now moving on to the third one. Third one is also, I think, a similar question. It's exactly the same question. So perhaps you can guide me with this one. Quickly we will run through this. It's the same question, I think, with slightly changed data. That's it. So okay, yeah, exactly the same question. So in this case the data is different, so I'll just quickly go through this. So the singular values sigma 1 is 2, sigma 2 is 1, and clearly sigma 1 is greater than sigma 2. Okay, did I write that before? Yeah, I've mentioned that. Okay, and the noise power, which is a sigma squared, is 16 here. Total power is capital P equals to 20 here, and again the assumption is that I assume positive power is allocated to both the channels. So Pi, so which means Pi is greater than 0 for I equals to 1 and 2, because there are I can take only two values in this case. Okay, so as we saw that Pi is given by 1 by lambda tilde minus sigma squared by sigma I squared, and again we will do the same steps. So P1 is nothing but 1 by lambda tilde minus sigma squared by sigma 1 squared. So this is sigma squared is 16 in this case, the noise power, and sigma 1 is 4. No, sorry, sigma 1 is 2, I think. Sigma 1 is 2, and sigma 1 squared will give me 4. So this is, and again I am labeling this as equation 1. Similarly, you find P2. P2 will be, sigma 2 is I think 1, so 1 squared is 1 itself, so this is 1 by lambda tilde minus 16. Okay, and again we'll use, yeah,
16 and 4, right?
16, yeah, 16 and 4. So P1 is 1 by lambda tilde minus 4 and P2 is 1 by lambda tilde minus 16. Just we have substituted the values. So sigma 1 and sigma 2 are given and sigma square is also given. Okay, so and now we'll use the total power constraint as before. So which tells me that the sum of the powers must be equal to the total power. So what do I get? And total power in this case is 20. Okay, so I wrote this step from equation 1 and 2. Okay, so what do I get here? 1, so I'll have 2 by lambda tilde is equal to 40. So which gives me 1 by lambda tilde equals to 20. Now again I'll substitute this. Substituting 1 by lambda tilde equals to 20 in equation 1 and 2 will get the powers. So P1 is 1 by lambda tilde minus 4. So this is 20 minus 4, which is 16, and P2 was 1 by lambda tilde minus 16. So this is 20 minus 16, which is 4, and so P1 is 16 and P2 is 4. Their sum is 20, which is the total power, and this is again my optimal MIMO channel power allocation. This is MIMO, this is I. Okay, this is multiple input, multiple output. So and here also if you see, like, P1 is greater than P2, which makes sense because sigma 1 is greater than sigma 2. Okay, and so the correct answer is option A. Okay, now let's come to the fourth question. So far, is it clear? Any doubt so far?
No, it's okay.
Okay, then let's continue. I'll just quickly check the chat window. Okay, there's no chat, fine. Okay, in the fourth question, we are given a linear model described by y bar equals to hx bar plus n bar, where H is your channel matrix, it's a 4x2 matrix, y bar is your you can treat it as a received vector or a noisy measurement. Okay, so you are sending x bar from the transmitter, let's say, and it is getting affected by the channel, which is the H as a multiplicative factor, and also it is getting transformed by the channel matrix, and also the noise is acting, which is n bar, right? It's additive noise, and you are getting a noisy outcome at the receiver, which is y bar. And also assume that x bar and n bar are uncorrelated, which is usually the case mostly. The transmitted signal and the noise you are considering as uncorrelated. And what else are given here is the covariance for this x bar, and the mathematical definition of covariance is that, I mean, why is it called covariance? Like, I mean, because it's like the I mean, it's done between the two same uh, signals essentially, because we are taking x bar, expectation of x bar transpose. So, and I mean, usually if there are like two different vectors, then it's usually called the cross covariance, right? For example, rxy or ryx. But in this case we are doing rxx, so expectation of x bar transpose, and that is the matrix which is half times I identity. Okay, that's I is like the notation for identity. And the noise covariance, similarly, expectation of n bar transpose is equal to identity. So this is given to you. Now, given all this information, you have to find the linear minimum mean square error, which is LMMSE, estimate of x bar for this system. Okay, and I'll assume that you have gone through the lectures of week 7, in which the LMMSE estimator was discussed, and we have looked at the expression for the estimate, right? So particularly we looked at two scenarios. The first scenario was the relatively simpler scenario where like we have zero mean uh, vectors, right? So the expectation values was 0. And on the more general case, it could have been like non-zero expectation or non-zero mean, and in that case we subtracted the mean and on, and we finally eventually landed up in a expression of the the estimator, LMMSE estimator. And if you recall, it was given by some rxy times ryy inverse times y bar minus the mean of y bar plus mean of x bar. I mean, it will be clear if I write it down. So we'll use that formula that has already been derived in the lectures and solve for this estimate. Okay. So I think this is question number 4. So the linear model that is given to you is y bar equals to h x bar plus n bar, right? And what else is given? X bar n bar are uncorrelated. Okay, and this matrix, these are specified. So your H channel matrix is given as follows, and your y bar is given by minus 1 3 minus 2 1. Okay, and you can quickly tell me what should be, what do you expect the dimension of x bar to be, or its estimate to be, given this information? If H is 4 cross 2, if y bar is 4 cross 1, then what should be the dimension of x bar naturally? H is 4 cross 2, y bar is 4 cross 1. So what should be my dimension of x bar for this model to be dimensionally correct?
2 cross 4.
Is it 2 cross 4?
H inverse
2 cross 1.
2 cross 1, right?
2 cross cross 2.
So if you multiply 4 cross 2 with 2 cross 1, then the result will be 4 cross 1. That's what we need, right?
Right.
So yeah, so we are getting a vector at the end, but if you multiply 4 cross 2 with 2 cross 4, we will end up with a 4 cross 4 matrix,
4 cross.
and the noise vector is also 4 cross 1. So this dimensionally makes sense.
Right.
And now, yeah, and now so the additional information that we have given, I mean, it's not the additional information, it's required. So the covariance, as I said, expectation of x transpose, it also has an alternate notation rxx. Okay, so we are taking the what can I say, the correlation. It's kind of correlation, but it's actually covariance. So we are taking the same two signals, x and x, and I am trying to find the covariance between them. So that's why rxx, and this is given as half times identity. And for the noise also I have given this information for the noise. So basically instead of x bar I take n bar. So that is expectation of n transpose. So you can also write this as rnn also, and that is equal to identity. Yeah, I think someone's mic is on. Can you please turn it off? Yeah, thank you. So rnn is given as 1, right, the noise covariance, and we are asked to find the linear minimum mean square error, which is LMMSE, estimate of x bar. Okay, and let me denote it by some x hat. Usually, I mean, we use this hat or cap for representing estimate. Okay, it's just an estimate. It might be, you know, having some error, some deviation from the actual true value of what x bar was originally transmitted. So this is what we are interested in finding. And so as I said, we have seen you know how to solve for this, and the solution, if you recall, I think, which lecture was this one? I think the last lecture of week 7 perhaps, which is I think the lecture 36. So if you recall lecture 36, we have looked that okay, x bar is actually given by, it's for the more general case, right, it's given by rxy. So as I said, what is rxy? It's actually the cross covariance between x and y. Rxx is the covariance of x, Ryy is the covariance of y, Rxy and Ryx are the cross covariance because they are the cross terms, right? So this is given by Rxy, Ryy inverse, and these are matrices, right? These are covariance matrices times your y bar minus mu bar y, which is the like the mean of y bar, plus the mean of x bar. So the notation is like this: mu is the mean. Okay, so this is my LMMSE estimate of x bar. So for finding x hat, we need to find all these quantities involved here. Y bar we already know, it's given in the question. Okay, so okay, so what can we do here? Okay, okay, and for this question, we will also assume that I'm also assuming that my means, right, my mu bar x, which is expectation of x, this is 0, and my expectation of noise, which is mu bar n, is also 0. I am assuming this. So this is the more general setting. Okay, so I'll take this assumption. Okay, I'll maybe add this information in the question also, so to simplify the thing. So for mu bar x equal to mu bar n equal to 0, like for the 0 mean vectors, your so before I do that, okay, so if x bar and n bar have 0 means, so then what can you say about the mean of y? Your mu bar y is expectation of y bar, right? And the linear model says that y bar is equals to h x bar plus n bar. So this is the expectation of h x bar plus n bar. Okay, so h comes out, it's a constant matrix, expectation of x bar plus expectation of n bar. So this is h times mu x bar plus mu bar n, and this is 0, right? This is also 0. This is by our assumption, both these are 0, so this is 0 plus 0, which is also 0. Okay, so x bar now reduces to, if you have mu bar y is 0, mu x bar as 0, then it simply reduces to r xy r yy inverse times your y vector, y bar. Okay, this is what you are interested in. Okay, now let's try to solve this. So at first, how do you find rxy? Remember in the question, how rx is calculated? It's expectation of x transpose. Okay, so that's how rx is calculated. So naturally, how our xy is calculated? It is expectation of x y transpose. More generally, the formula is x bar minus the mean of x bar times y bar minus mean of y bar whole transpose. That's the general formula of covariance. But in our case, both this mu x bar and mu y bar are 0, so it boils down to, it's simply x bar y bar transpose. Okay, and how can I further simplify this? This is expectation of x bar, and what is y bar? Y bar is h x bar plus n bar whole transpose. Correct? So this is expectation of, if I split this summation, okay, this is okay, just a second. So I know I can take the transpose term by term, and linearity holds. So this is like h x bar whole transpose plus n bar transpose. Okay, it's like this. Now what is this? This is expectation of x bar, and inside this bracket, so what is h x bar whole transpose?
X transpose H transpose.
Exactly, because in general we know that if we have a b transpose, the whole transpose, that is b transpose times a transpose. Okay, the sequence is reversed. So this is nothing but x bar transpose into h transpose, plus we have this term sitting here, this. Okay, maybe I will go to the next page. Okay, so here we are. So this is expectation of, now I can multiply them, right? This is plus okay. Now by linearity of expectation, I can actually break this summation into two parts, into sum of two expectations, right? This is like this, right? And here H transpose is a constant metric, so it will come out of the expectation like this, right? And I have expectation of x bar in transpose. So what about this guy? Do you recognize this guy? Expectation of x transpose. This is simply your covariance of x, right?
RXX.
Rxx, and it is actually given also. It is half times identity. And what can you tell about this term? Expectation of x n transpose. So you see this is a covariance of, this is a cross covariance of x and n, right? And in the question it is mentioned that x and n are uncorrelated. So this term will actually vanish. Why this is vanishing? Because this is like Rxn, and in the question it is mentioned that x and n are uncorrelated. So this is Rxx times H transpose, and Rxx is given as half times identity, so this is simply your half H transpose. Okay, this is Rxy. So what did we get so far? Rxy is equals to half H transpose. Fine. Now we also need to find Ryy, okay, and also take its inverse. So Ryy is the covariance of y. So we will solve it similarly. So by definition, this is expectation of, so I have to write it completely. This is like this, transpose, correct? And in general, for a complex vector or complex matrices, this transpose has to be replaced by Hermitian. Remember, Hermitian is the complex conjugate as well as transpose, right? The transpose conjugate. So that will apply whenever there are complex numbers involved. But here all the entries in H and Y, they're real, right? So I'm skipping that Hermitian and I can straight away take the transpose. So just a word of caution. So I'll mention somewhere, maybe here only. I'll just mention as a side note. So transpose, which is T, has to be replaced by Hermitian, okay, which is H. And I hope what you know by what is meant by Hermitian is the transpose conjugate for complex, right, for complex vectors or matrices. So just a word of caution. Okay, now let's simplify this. So y this mu y bar is already 0, right? We have seen. So this is ultimately this, and now I can actually write y bar as hx bar plus n bar, then also hx bar plus n bar, the transpose, and then I can solve this, right? And if I okay, now there will be 4 terms inside expectation. So this is h x bar transpose h transpose plus h x bar n transpose plus n bar x transpose h transpose plus n bar transpose. Okay, and now what about the first term? I can take the h terms outside the expectations, right? So if I write it term by term, then this is h comes out, so expectation of x transpose h transpose, that's my first term. Then I have this plus expectation of n x transpose to h transpose plus expectation of n transpose. Okay, now again, so this guy is Rxx, right? And this, what is this? This is 0, right? Because x and n are uncorrelated, so the cross covariance terms would be 0, right? Similarly, this is also 0. And what about this guy? This is the covariance of the noise. which is given as identity in the question. You see this I. So this is actually your RNN, which is also identity given in the question, and this is given as half times identity. Okay, so what do we get here? H into half times identity times H transpose. So these two terms will actually vanish. This vanishes and this vanishes. We are left with only two terms, plus this is identity. So how much is this? Half H transpose plus identity. Hope I have written it correctly. Yeah, I guess I have written it correctly. So okay, so this was our calculation for RYY, right? RYY we got of HH transpose plus identity. So RYY we have, RXY also we have calculated. Now we can plug in these values in this formula for estimate of X, LMMSE estimate of X, right? Y bar also we know from the question. So just we have to plug these things in the formula. Okay. So this is your RXY RYY inverse Y bar. So what is my RXY? We have calculated that it is half H transpose. And what is RYY? RYY we just now calculated that it is half HH transpose plus identity, this whole inverse times Y bar. Okay. Now there are still some calculations left to be done, especially this guy sitting in the middle, because it involves computation of an inverse, right? So let's do it step by step. So what about HH transpose? H is given as 1 1 1 1 minus 1 1 1 minus 1, okay, and its transpose is this, right? So this is 4 cross 2, this is 2 cross 4. What you will get is a 4 cross 4, and you can verify that you will get 4 cross 4, which is this. Okay. Now we have to find half HH transpose plus identity. That's my RYY, right, in the expression. So if you do that, scale it by half and add identity matrix, you will get 2 0 0 1 0 2 1 0 0 1 2 0 1 0 0 2. Okay. Now we have to find this guy's inverse. So find its inverse. Okay. I mean that seems a bit challenging because it's a 4 cross 1 matrix, right? Sorry, 4 cross 4 matrix, right? In generally we are used to, you know, if it's a 2 cross 2, it's just one step. We can easily find its inverse. For 3 cross 3 also, okay, some work has to be done, but 4 cross 4 is a slightly big matrix. But nevertheless, one strategy could be, okay, I can straight away, I already have the values, I can write it directly, but let's solve it together. So what I will use is the Gaussian elimination, right, the row operation. So this method is called as Gauss-Jordan method, Gauss-Jordan elimination, whatever. Okay. So So what I do is, this is actually my, what this is my RYY, right? So what I will do is, in this Gauss Jordan method, I have to find RYY inverse. Okay, so first what I will do is, I will form an augmented matrix, right? I'll write RYY and I'll stack it or concatenate with an identity matrix of the same size, in this case 4 cross 4. Okay, so I'll start with this. So this is called as augmented matrix, right? And I have described all these things in details. What is an augmented matrix, what are valid row operations, what is Gaussian elimination, you know, all these things, and how to find the inverse in different ways. You can also take the adjoint or adjacent of the matrix, divide by the determinant to get the inverse, provided the determinant is non-zero, right? Because every matrix is not necessarily invertible. And you can also use these row operations, which we will use right now using the Gauss Jordan method. So you can refer to my previous videos in case you haven't watched them. So we start with this, and using row operations, I will arrive at the form like this. Okay, so my left half will become identity and my right half will become my inverse of the matrix. Okay, the reason is that, you know, every row operation is actually equivalent to multiplying the matrix with another elementary matrix, and it is called elementary matrix because it is obtained by performing a single row operation on the identity matrix. So every row operation, let's say R1 changes to R1 plus R2, whatever, that is equivalent to multiplying with a matrix. That's an elementary matrix. So using some sequence of matrix multiplications, if you are arriving from, consider the left half, if you are arriving from RYY to I, like this, if you consider only the left portion, from RYY you are arriving at I using some sequence of matrix multiplications. Then from I you should go to RYY inverse, right? Because RYY, from RYY to identity, it is possible only if that gets multiplied by RYY inverse, right? And similarly, the same thing happens for identity also. If you start with identity, it goes to simply RYY inverse, right? That is how it's mapping to identity augmented with RYY inverse. Okay. Okay, so that is the idea. So RYY. So any doubts so far? Okay, great. So my RYY, the augmented matrix that I can form is okay, and I have to take the identity matrix of the same size. Okay, I'll have to, maybe I'll write this slightly to the left. Okay. So what is the identity? The 4 cross 4 identity in this case. All right. So remember, we have to map this left part to identity, and automatically this right part will become the inverse of RYY. Okay, So what could be the first step? I mean, in order to convert this to identity is like it's already in the row echelon form, or rather the reduced row echelon form, right? So first what I can do is I can make this guy, this one here in the fourth row, this I can vanish. And how do I do that? I will actually do, if I do R4 getting mapped to R4 maps to R4 minus half R1, then what will I get is the first three rows will remain unchanged, the fourth row, what does the fourth row become? Can you help me with the entries? R4 changes to R4 minus half R1. Yeah, if I do this row operation, what will my fourth row become?
0, 0, 0,
3 by 2, right?
yes.
So 3 by 2, and you also have to do for the right side as well, don't forget that. So this will become minus half, this is 0,
0,
0,
0.
and it's 1. Okay, so now we are quite close, and next what I can do is I will try to modify R3. R3 goes to R3 minus, I mean, I am assuming that you are familiar with this Gaussian elimination process, but still I am, writing down. So I am doing R3 changes to R3 minus half R2. And again, the reason behind this is simple, because I want to eliminate this one here. Okay, I want to make this disappear. I want to change this 1 to 0 actually, because then only I will get a diagonal form which is required for the identity, right? That's what I want on the left side. So if I do that, then what do I have here? This now vanishes. And this on the right side it becomes this. Fourth row is unchanged. Right. Now what else we have to do? You see, I have this one here, right? That is a term sitting in the off diagonal, right? So I want to make that 0 as well, because I want identity here, and identity, as you know, is just a diagonal matrix with only ones along the diagonal. So I have to make that 1 0. So can you suggest me a row operation that will make that entry 0? Can you think of a row operation? I have to change my R2 here, because that one which I have circled is lying in the second row. And yeah, go ahead.
R3 minus 2 by 3 or
Yeah, I mean, if you do R2 changes to R2 minus 2 by 3 R3,
yeah.
then it will
2
become
is
0.
equal to yes, yes.
Correct. So R2 changes to R2 minus 2 by 3 R3. If I do this, and you can refer to my previous videos, what are like the valid row operations. You can't just do anything, right? There are certain operations which are valid row operations. Okay, so, and by valid I mean these are allowed, and it ensures that the what you are doing at the end of the day, you have a system of equations that you are solving, and in this case you are having a matrix, you are trying to invert it, and that also is a solving linear equations. So these row operations ensure that the solution to the system of linear equations does not change. That is the thing, that is why we are able to simplify the process, reduce, I mean, introduce sparsity by making some entries 0, simplifying our set of equations, so that the solution does not change, but the process gets simplified, the calculation becomes simplified. So anyways, if we do this, what do I have? This now becomes 0, and this term you can verify, this will become 4/3, and this will become minus 2/3. This stays at 0, and the other rows are unchanged. Okay, okay, another one more thing is left, this guy here, this is sitting in the off diagonal, and I have to make this disappear, I have to make this 0. So again I can use the fourth row for this, right? So I can use the operation R1 changes to R1 minus 2/3 R4, then I can make that one disappear. So I'll go to the next page. So what I am doing is R1 changes to R1 minus 2/3 R4. So what I will get, you can verify, is this. Okay, I mean these are distinct, these are disjoint. Okay, these are not, just to avoid confusion, this is okay. 0 0 3 by 2 0 0 minus half 1 0 0 0 0 3 by 2 minus half 0 0 1. Okay, now you see we have a diagonal structure here on the left side. All we have to do is just scale them appropriately, right? So R1 has to be scaled by 2, right? I want to change this 2 to 1. All the diagonal elements must be 1 in order for that to be identity. I have to scale R2 by again 2. For R3 I have to do this. For R4 also I have to do this. Sorry, this is R4, right? So on doing this, my left half will actually become the identity, 4x4 identity, which I want, and my right half will become So you see, this is exactly your identity, which implies that this part will be actually your inverse, right? RYY inverse. This is your RYY inverse. This is RYY inverse, right? So therefore, what is my x hat? My x hat was this, right? Half H transpose, this whole thing, this RYY inverse times y bar. Right, this guy. So this inverse we just calculated, right? So this is half, and H transpose is simply this inverse we just found. Okay, so this thing. 0, 2/3, minus 1/3, 0, 0, 1/3. And if you want to actually verify whether it's the inverse or not, you can take this RYY inverse, you can multiply with RYY, okay, in either direction, RYY times RYY inverse or RYY inverse times RYY. You should get the 4x4 identity. You can verify that. Okay, and this is 1/3, minus 1/3, 0, 0, 2/3. This, and our y vector, it is already given in the question, this. So this is 2 cross 4, this is 4 cross 4, this is 4 cross 1, right? So hopefully you can calculate this, no issue in the calculation, hopefully. So if you do that, you will arrive at a 2 cross 1 vector, right? And that is nothing but your 1/6, 1/6, and you can pull out 1/6 outside, and this is 1, 1. And if you check with the options, it is option A. Okay, so a lengthy problem, but any doubt so far? All we have done is just the calculation, I mean, it was a lengthy calculation, but yeah, we use the LMMSE estimator formula, and and for that we had to calculate these covariance matrices. That's all. I think this might be explained in the future weeks in more detail. Maybe you can do this relatively quicker, but yeah, if there are any doubts, you can ask me, or else I will proceed for the next one.
Okay, sir.
Okay. Okay, so moving on to the next one. Okay, again, this is the application of the music algorithm. Okay, so we have a multiple, so we are looking at fifth question. We have a multiple antenna, like a uniform linear array of antennas with L equals to 2 antennas. So it's a 2 antenna system. It's like the very simple scenario, and the antenna spacing is denoted by d, small d, and the signal wavelength, as you know, is denoted by lambda, and the relation between them is that their ratio is equal to half, dy lambda equals to half. The array response vector a bar of theta. Remember that array response vector, it actually contained the, you know, exponential, I mean the phase terms, right, the involving theta, right, if you remember. It was also of size L cross 1. In this case L is 2, so it's a 2 cross 1 vector. So this captures the, you know, direction of arrivals and so on. So we are asked, like, the array response vector a bar of theta corresponding to angle of arrival theta equals to pi by 3 is what? And you see the options, they are all 2 cross 1, which is naturally expected because, I mean, L is 2, so I mean the array response vector has to be 2 cross 1, L cross 1, right? Okay, so this also we know, right? I mean, we have looked at the, you know, maths. So the setting was like this, like, again recall lecture 33 where music algorithm was introduced. So this was the setting, if you remember. There is a receiver Rx, okay, and let's say there is some target aircraft, let's say, approaching. Okay, assume this is a aircraft, okay, although it doesn't look like an aircraft. So let's say this is your aircraft or source, okay, and this receiver has two antennas, L equals to 2 here, okay. So this is L equals to 2 antennas, and so this is the signal this is the signal that is coming, being transmitted, and similarly, like, we'll have like this. So this direction, and by the way, the antenna spacing, the spacing between the two antennas is small d, right? So so this angle is actually the direction of arrival of the transmitted signal, let's say at an angle theta. So this angle is theta, right? Now I know that this distance is d. Now if you drop a perpendicular like this distance will be d cos theta, and d cos theta determines your difference in the propagation. Let's say for the first signal to arrive and the delay for the second signal to arrive, that is governed by this, you know, difference in the propagation length, right, this given by this d cos theta. So that's the delay parameter here, and in general, like, the signal that is transmitted is x of t e power j 2 pi fc t. It's transmitted at the carrier frequency, right? So, and plus some noise term as well. So your fc is your the carrier frequency, right? And so what I meant is, so if the first path arrives with this phase, then I mean with this phase, yeah, then the second path, which I have shown parallelly below, will be having a delay of d cos theta. So this d cos theta will sit in the phase term of this e power j whatever. So that will be delayed by a path of like d cos theta amount. Okay, and those delays are actually captured in that array response vector. If you remember, it is also known as array steering vector as well. So the parameters here, d is my spacing between the antenna, so antenna spacing. Okay, in general, like, you can have multiple antennas as well. Let's say L, in general, L number of antennas, and the separation will be uniform. Lambda is my signal wavelength, right? Signal wavelength, and we know the relation between lambda and fc. So fc is given by c by lambda, right? We know this is a very well known formula, and where c is the speed of light in air or vacuum. I mean, essentially we are assuming that, okay, the signal is an electromagnetic wave which travels at the speed of light, and the medium is air or vacuum, so it's the speed of light. Okay, and the theta as drawn in this diagram. And by the way, this d by lambda, the ratio is given as half. Okay, so this is given, and theta is my angle of arrival, which has been shown in the diagram, and that is also given as pi by 3. This is also given. Okay, for this theta equals to pi by 3, what is my array response vector? So if I go to the next page, so if you recall, the array response vector or the array steering vector is given by a bar of theta. It will capture all the delay terms, the theta terms, right? And it was given by this, the general form was this 1. It starts with 1, then it captures the first delay term, right, which is e power minus j k cos theta. I'll come to what is k. And similarly, if it gets like 2 times delayed, then it's e power minus j 2k cos theta. I mean, these are corresponding to the L paths, right? You will have L paths for the L receiving antennas, right? So, and it gets delayed more and more. Okay, and then finally the Lth term of this vector would be e power minus j L minus 1 k cos theta. So by the way, j is like the square root of minus 1, right? So this j is not any index or anything. J is the iota. Sometimes we use I as well. Okay, just make sure. And where, as I was saying, this k, it is 2 pi d by lambda. Okay, we have seen this in the lectures. Just recall lecture 33. And here L is 2 antenna system. So therefore my a bar of theta will have only 2 elements, right? It's a 2 cross 1 vector. So the first entry is anyways 1. The second entry will be e power minus j k cos theta. Minus j k cos theta. And what is k? It is 2 pi d by lambda. So this is 1, this is minus e power minus j, k is 2 pi d by lambda cos theta. Okay, I mean, and this derivation was also very simple actually. I mean, you know, right? You will have like corresponding to the corresponding to the L equals to 2 in this case, two antennas at the receiver, you will have two, incoming vectors, right? And each transmitted vector is delayed by some different components, right? Um, and you can form a system of equations here also. And all we have done is we have actually captured in a matrix form, and the vector, this vector array response vector captures the delay amount, and so we can multiply this to your x of t or x of t term, and also there will be an additive noise term which will always be there. That will give you your y bar vector actually. So as simple as that. So now if you simplify this further, so you know d by lambda is 1, sorry, d by lambda is half, it is given. So I've written it here in this box. D by lambda is half, and theta is also pi by 3, it is given. Theta is pi by 3. So just plug in the values. This is e power minus j 2 pi d by lambda is half times cos pi by 3 so this is 1. So this 2 gets cancelled. E power minus j pi, what is cos pi by 3? It is simply half. Okay, so this is 1 e power minus j pi by 2. What is e power minus j pi by 2? It is, yeah, tell me quickly, what is e power minus j pi by 2? What is this term? What is the value of e power minus j pi by 2? It's simply minus j, right? I mean, in general, you know the Euler's formula, right? E power j theta, it's simply cos theta plus j sin theta. Correct? It represents any point on the unit circle, the coordinates being cos theta comma sin theta. So naturally, what is e power, if you put theta equals to minus pi by 2, e power minus j pi by 2 will give you cos minus pi by 2 plus j sin minus pi by 2. What is cos minus pi by 2? Cos minus theta is same as cos theta, but cos pi by 2 is 0, so cos minus pi by 2 is also 0. And what is sine of minus x or sine of minus theta is the same as minus of sine theta, and sine pi by 2 is equal to 1, so we'll get minus j, so this is minus j, so this is 1 minus j. Okay, and this j is the square root of identity, remember, j is the square root of identity. So 1 minus j, that is our array response vector, and it is option C. So the answer is option C. Okay, any doubts? Any doubts on this question?
Yes.
Okay, great. Then let's move on to our last problem for today. Okay, and this is also based on the linear minimum mean square error estimator. So we have solved one example. Let's look at another example. So consider the random variable y denoting the noisy measurement of the angular position x of an antenna. Okay, so x is also another random variable, and it represents the angular position of an antenna, and y is the noisy measurement of x. Okay, and the equation is characterized by y equals to x plus w, or you can simply think of it as like a normal communication model where we are trying to measure or estimate x, right, and the noisy measurement of x is reflected in y, right. Y is the noisy measurement of x, and what is the noise? This w, this additive noise term is w sitting in this equation, right. So y equals to x plus w, where w is the additive noise, right, and y is the noisy measurement of x. Assume that the noise is independent of the angular position, so meaning that let us assume x and w are independent random variables. So the noise and the random variable x, which represents angular position of an antenna, these two are independent random variables, and the random variable x is uniformly distributed in the interval -1, 1. So it has a uniform distribution in this interval, and the random variable w, which is the noise, is also uniformly distributed in the interval -2 to 2. Given this information, we have to find the LMMSE, the linear minimum mean square error estimator of x in terms of y. And again, we have to assume that this x and y are individually IID random variables, identically and independently distributed random variables. They are individually IID. Okay, that's also given. And so again, we know the formula for LMMSE, which we have used in the previous question also. So so of course x has to be estimated, the estimate of x has to be represented in terms of y only, right. So we have wrote down, right, r x y times r y y inverse, and there was that y bar, right. So in this case they are random variables here, but the process is the same. I mean, you have to estimate the x in terms of y, express that in terms of y. Okay, so let's see. So this is the 6th question and the last question for today. So what we have is this system, y equals to x plus w. Okay, this w is my additive noise, and this x is what I want to estimate. It denotes the antenna position, and y is my, of course, noisy measurement of x, and it is given that x and w are independent random variables. Given, and the distribution of x and w are also given. X is distributed as, so this denotes the is distributed as, it has a uniform distribution, so I am writing it as like this, -1 to 1. In this interval it is uniformly distributed. Similarly, w is also having a uniform distribution in the interval -2 to 2. Okay, can you tell me about the mean or the expectation of these two random variables x and w? Straight away, can you tell me, just by looking at the description of their distributions? What do you expect of their mean value? Okay, so let we usually use small f, right, for denoting the probability density functions, or PDF, right? So and typically we use like this. For the subscript we use the random variable, and inside the parenthesis we use the values that the random variables can take. So this is small x inside the first brackets, and on the subscript we have the random variable capital X. Okay, and small f is used for PDF. So let f of x, f x of x and f w of small w denote the probability density functions. Okay, the PDFs, or maybe PDF. Okay, PDF of the random variables x and w respectively. So how does a uniform distribution look like? So in general, if I tell you that and here it's a continuous like random variable. So in general, if I tell you a random variable is uniformly distributed from some range a to b, let's say I have a random variable r which is uniformly distributed from a to b. Okay, so how do you characterize its PDF? What does the plot look like? Let's say this is somewhere a and this is somewhere b. So it is uniform, it is flat like this from a to b. Okay, and what is the height of this distribution? So this is my FRR of R, the PDF of R, and this is the R, the values that R can take. So remember the property. Yeah, go ahead.
1 by 2?
1 by 2.
Oh no.
Here
1 by b minus a.
Yeah, exactly. So 1 by b minus a. And why is that?
Integral of a to b to it's
Exactly.
1.
Exactly. So we have to remember that the property of PDF says that the area under this PDF, which is nothing but this integral from minus infinity to infinity, in this case from a to b, should be equal to 1. So I mean, you know, right? I mean, sum of probabilities has to be 1. Think it like that also. So the area under this graph, area under the PDF is equal to 1. So that is possible only if the area of this rectangle is equal to 1. So the height, if the width is b minus a, so this width is b minus a, right? And so for that the height has to be 1 by b minus a, right? So this is how a uniform distribution looks like. Now hopefully you can plot fx of x and fy of y, which are the PDFs of x and y. So what does fx of x look like? This is fx of x. It is uniformly distributed from -1 to 1. So the first question which I asked you, what is the mean? What are the means or expectations of x and y? Just by looking at the distribution you should be able to tell me. See, they are uniformly distributed from -1 to +1. So they're centered around 0, right? So the mean naturally is expected to be 0. If I draw the diagram, it will be more clear. So this x is uniformly distributed from -1 to +1. So in between these lies 0. So this is the uniform distribution, and just tell me the height of this rectangle.
1/2.
1/2. Thank you. So this is 1/2, just to make sure that the area is 1. And what is FW of W? That is distributed from -2 to +2. So let me to go from here to here, let's say. I mean, it's not drawn to scale, but yeah, from -2 to 2. And again, this height will be, so the width is 4, so this height has to be 1/4. Now naturally their expected value, or the mean lies somewhere in the middle. So, and these two are both individually 0, right? So the average value, I mean, this has a positive, this has a negative part, this has equal positive part. So I mean, you expect the mean to be 0. They are centered around 0. Or mathematically, if you want to find the mean, you can actually calculate that as well using the mathematical formula. But by the way, I mean, why do we care about the means? Because we need them, right, for finding the estimate. Our original problem is to find the LMMSE estimate of x in terms of y equals to, let's say, some x hat, which is what we need to find. And as we are familiar with the formula, x hat is given by r x y r y y. Since I have random variables which are uppercase, which are denoted using uppercase characters, so I am sticking to that notation. R y y inverse times, this is the more general formula, remember, y minus the expectation of y plus expectation of x, right? This is a general, more general LMMSE estimator when the random variables have non-zero means. So where did it go? Yeah, this one, this what I have written here. So this is the more general. See, I have labeled it as general. So this same thing I am writing here. The only thing is that here we have random variables. Okay, so I am using capital letters. So yeah, this thing. But so for that I need expectation of x as well as expectation of y. So what is expectation of x, or the mean value of x? As I said, from the uniform distribution centered around 0, you can easily claim that it's 0. But if you want to calculate it, it is basically calculated as x times fx of x, the PDF, right? You perform this integration from minus infinity to infinity. That's your expectation. That's the definition of expectation, right? I mean, if you are not familiar with these things, you can maybe do a brush up of the probability course. So this is nothing but, so fx of x is the PDF of x that is effectively non-zero from the interval -1 to 1. So instead of minus infinity to infinity, we can just integrate from -1 to 1 x, and what is fx of x in that interval? It is half. So this is times half dx. Okay. So this is nothing but this. What is this equal to? If you substitute the upper limit and lower limit, zero. That's what you expect, right? I just told you straight away. I mean, in general, if you have a uniform distribution centered around 0, you calculated expectation, you expect it to be 0 naturally. That's what you got. And similarly, what about the expectation of W? That also is expected to be 0 because that is also centered around 0, right? Uniformly from -2 to +2. But let us calculate anyways. So again, by formula, this is this guy here, right? So but again, I can only integrate from -2 to 2, -2 to 2 W, and my PDF during that interval is 1/4, right? It's taking the value 1/4 times dW. So this is your how much do you get here? Basically, integration of W gives you W square by 2, and there is also a factor of 4, so W square by 8. And again, if you just substitute the upper and lower limits, this is again 0. So both x and W are 0 mean random variables. We also need to find expectation of y, because that is present in the formula of x hat, the estimate. What is the expectation of y? What is the expectation of y? Y is nothing but y is basically x plus W, right? That's our model. That is the model originally. See? And we just now saw that both x and W have 0 means. So this is 0, this is also 0, so this is 0. So now this estimate, the formula for estimate, can be simplified to this. This is nothing but Rxy Ryy inverse times y, right? Because the other two terms, the expectations will disappear, they are 0. This is what I need to compute. I mean, I effectively need to compute this part, right? So let's do that. So again, what is Rxy? It's the cross covariance, remember? So this is expectation of x minus expectation of x, then y minus expectation of y, but we have to take the transpose. But in general, we have to take the Hermitian. Yeah. But in this case, since like x and y, they are like real, as you can see, the PDFs, they are real, right? I mean, they are distributed in along the real axis, right? So we can just use simply transpose. That's fine. Okay, generally you can use Hermitian, it's the same thing for the more general case of complex entries. So yeah, but what is this both these expectations are 0. So this is x y transpose. So this is again, what is y? It is simply x plus w, right? So this is x transpose plus x w transpose. So this is expectation of x transpose plus expectation of x w transpose. Okay, so what can you comment about these terms here? First of all, let us consider this term. This is like the cross covariance of x and w. This is like r x y, and you see in the question it is given that x and w are independent random variables. X and w are independent random variables, and you know that independence implies uncorrelatedness, but the converse is not necessarily true. But if they are independent, if two random variables are independent, they are definitely uncorrelated. So if x and w are independent, they are definitely uncorrelated, so their cross covariance will be 0 because they are uncorrelated. So since the reason is, it is given that x and y are independent, which means they are also uncorrelated, but the converse is not true. Okay, the converse holds only under a special condition for a jointly Gaussian case, but I am not going into the details of that. Okay, and now what is this guy here? This is rxx. Okay, so effectively we have rxx, and on top of that it is told that okay, x and w, you see read the last line, x and w are individually IID. So, and if you recall the lecture notes of the past weeks, for any IID random variable, the covariance matrix is a diagonal matrix. You remember? This is of the form sigma squared identity, if you remember, for an IID random variable. So this is some sigma x squared identity, where sigma x squared is my variance of the random variable x, and why is this equal to sigma square identity? Since x is IID. Okay, so this is my rxy. So now let us find sigma x squared. So sigma x squared is nothing but my variance of x. As I said, variance of x is sigma x squared, and you know variance of x is given by the mean squared value minus the square of mean. So it has this formula, right? Expectation of x squared minus expectation of x the whole square, right? This is the one of the known formulas for variance. This is the mean squared value, the mean of the squared value minus the square of the mean value, right? Mean of squared value minus mean value squared, that gives you the variance. Okay, I mean, if there is no doubt, I'll assume like people are on the same page if there are no queries. So but this term here, expectation of x, we saw that this is 0, right? We previously saw for the uniform distribution it turned out to be 0. So effectively we have expectation of x squared. Now how do we find expectation of x squared? It's again the same Like we calculated expectation of x, we can also do it similarly. So just instead of x there will be x squared, and my PDF will be there, right? Dx from minus infinity to infinity. And again my PDF, since it is effectively from -1 to 1, and the height, if you recall, was half, so this is dx, and this is nothing but x cubed by 6 from -1 to 1, and that is effectively 1/3. If you just substitute the upper and lower limits, you will get 1/3. So that is your variance of x. So sigma x squared equals to 1/3. Now that you know sigma x squared, you know rxy. So therefore you know rxy, which is sigma x squared times identity. So this is identity by 3. Okay, you know this. Now one step is done. What else do we need? We need ryy inverse. So how do we do ryy inverse? Let us first find ryy, which is the covariance of y. So ryy is nothing but expectation of y minus expectation of y is the first term, and we have to take its transpose. I mean in general Hermitian, but yeah. So what is this? But again we have calculated that y also has 0 mean, because x and w have individually 0 mean, and since y is x plus w, so it also has 0 mean. This is this term, and now I can write y as x plus w, because that's the given model. So this will be x transpose x w transpose plus w x transpose plus w transpose. Now what happens? Right? What about this? This is your rxx. Okay, just a second. Yeah, this is your rxx, and as we saw, this was that sigma squared x identity, right? Because x is IID. And what about these cross terms? These cross covariances, these are 0, right? Because this is nothing but my rxw, and x and y being independent, they are also uncorrelated, so their cross covariance is again 0. So what about this term, expectation of y, expectation of w transpose, that you can label as rww, right? And I can write it as some sigma w squared identity, where sigma w squared is the variance of the random variable w. Okay, so here where sigma w squared equals to variance of the random variable w. Okay, so what do I have effectively for ryy is this term sigma squared identity plus sigma w squared identity. Okay, sigma x squared we have already calculated before, it was 1/3, you see. So this is nothing but 1/3 identity plus sigma w squared identity. So let us now find sigma w squared. So which is my variance of w. So this is sigma w squared, and again I will use that formula for variance, which is the mean squared value minus the square of mean value. So this is expectation of w squared minus expectation of w squared, and again you know this is 0 because w is 0 mean. So this is expectation of w squared, and again by the integral formula you have this, and again the range will be effectively from -2 to 2 because that's how it is uniformly distributed, and the height of the rectangle was in the PDF it was 1/4, and that is w cube by 12 from -2 to 2. If you substitute you will get 4/3. Okay, so that is your variance of w, and you can plug this in the formula of RYY above. So therefore your RYY will become I/3 plus sigma w squared identity. Sigma w squared we just calculated, it is 4/3, so it is 4I/3. So overall this is 5I/3. So RYY also we calculated, this is 5I/3, but we have to take its inverse, right, because that's what is needed in the expression of the estimate. This is my estimate that I want to find. So we have to take the inverse of RYY. What is the inverse of this RYY? RYY is 5I/3. So what is its inverse?
Three by five I.
Exactly. So whenever you have a diagonal matrix, there's nothing to worry, you can just simply take the reciprocals of the diagonal entries along the principal diagonal, and that will give you the inverse. So RYY inverse is nothing but the inverse of 5I/3, which is simply 3/5 identity. Now we have all the tools, so we can find x hat, which is RXY RYY inverse times y, because the other expectations were, they vanished, right? I mean, this is effectively what we need to find. So RXY we have found, right, I/3, and RYY inverse also we have found, right? So I can just simply substitute them. RXY was I/3 we calculated, and this is inverse 3/5 identity times y. So this is 3 gets cancelled, identity times identity is the same, and this is 1/5. So my LMMSE estimate of x in terms of y is given by this. x hat equals to 1/5 of y. Okay, and if you check the options, it is the first option, option A. So answer is option A. Okay, okay. So with this we have come to the end of today's discussion. Hopefully it was helpful, and if there are any queries you can ask me, or else I'll stop the recording and sign off for today.
Okay, sir.
Thank you.
Okay, thank you. Then we'll meet again on next
Sure.
Friday,
Next.
6 p.m. Okay. So, okay, thank you.